Hello online viewers, welcome to our lecture video. In this lecture video, we are going to talk about trigonometric leveling. What is trigonometric leveling? What are the different classification of trigonometric leveling? And what are different cases of trigonometric leveling? We are going to talk everything about trigonometric leveling in this lecture video. And at the end of this lecture video, we are going to solve 5 different numericals based on different cases of trigonometric leveling to make the concept even more clear. And in the description box below, you can find the timestamps for this lecture video, so you can easily navigate throughout the video. So firstly, let's talk about trigonometric leveling. So what is trigonometric leveling? For the definition portion of trigonometric leveling, we can say that the trigonometric leveling is the process of determining the difference in elevation of stations, and this difference in elevation of stations is determined from observed vertical angles and known distances which are assumed to be either horizontal or geodetic lengths. So horizontal length simply means the short distance length which we can measure by our measuring tape, while geodetic lengths means such large lengths in which the earth cannot be considered as flat, and we need to consider the surface of the earth as a curve, and we need to have correction due to refraction. So firstly, to make this definition even more clear, let me draw a simple figure over here. So as you have over here, in trigonometric leveling, we are going to find the difference in elevation of stations. So for our trigonometric leveling, firstly what we are going to have is we are going to have a benchmark whose RL will be known. Next we'll set up an instrument at certain station, and firstly we'll sight at our benchmark, and we'll have our certain staff reading yes, and then we'll have our certain point which elevation is to be determined, and then we'll be sighting at that point, and we'll have our vertical angle alpha. This vertical angle which is determined by the help of our theodolite. And the next distance which we talked about, this is the distance between our instrument station and the object. This is known as station D, and this distance D is either measured with the help of is measured either directly with the help of any measuring with the measuring tape, or it is computed trigonometrically, or this distance is computed trigonometrically with the help of this observed vertical angle only. This definition will be more clear when we move throughout all the this definition will be more clearer when we move throughout all the cases of trigonometric leveling. So basically, to define trigonometric leveling, we'll use theodolite. We'll have our distance D. We'll have our vertical angle, and this distance D can be either horizontal for short distance and geodetic for long distance. Now for classification of trigonometric leveling. Depending upon horizontal distance between stations, trigonometric leveling may be classified into observation of heights and distance as plane survey, and observation of height and distances as geodetic survey. Depending upon this distance D, which is between the instrument station and our object, basing upon this D, we can have our trigonometric leveling as plane survey and geodetic survey. Plane survey is basically for our short distance in which we consider the surface of earth as flat, and geodetic survey when our distance D is very large, we cannot consider the surface of earth as flat anymore, and we need to have correction due to curvature, and correction due to refraction, so such a survey will be named as geodetic survey. So this is our basic classification of trigonometric leveling depending upon this distance D. Now we'll be mainly focusing upon the observation of heights and distances as plane survey, and this also has 3 sub classification. First is base of the object is accessible. So as you can see here, this is our object and this is its base. So we have our first condition where the base of the object is accessible. So what does accessible means? Accessible means that the distance D, this distance D can be measured easily by the help of our measuring tape, and it can be measured directly, and there are no any obstacles while reaching this. There are no any such obstacles while reaching the base of the object. Such is termed as, in such condition we are going to say that the base of the object is accessible. So this is our first condition. Second condition is where our base of object is inaccessible, which means there are certain obstacles because of which we cannot measure our distance D directly, and instrument stations and the elevated object are in the same vertical plane, which means that our instrument station, we can name this as C, and our elevated object, this is our elevated object, both are in the same vertical plane. So as you can see here, they are in the same vertical plane. This is our second sub case. And for our third case, again the base of the object is inaccessible, but in this case instrument stations and elevated object are not in the same vertical plane. So for this, what I can do is, this is going to be our instrument station, this is in our certain plane, and our object and our elevated object is going to be in, now our elevated object is our elevated object, it's going to be in a world different, it is going to be in a, it is going to be in a world different other level, world different vertical plane. So this will be more clear when we will be jumping it, when we will talk about it, so this is the basic introduction to trigonometric leveling. So firstly, now we'll talk about our first case where the base of our object is accessible. So now we have our first case where base of the object is accessible, and under this also we have two different cases where our object may be a vertical object, as you can see here, our object is vertically upward, or in our second case where our object is inclined, as you can see here, our object is inclined to the surface of the ground at certain angle. So we'll be talking about both of these cases. And as I talked before, base of the object is accessible. Here the term accessible means we can measure the distance between our instrument station and our object. This distance d, which is our distance between instrument station and the base of the object, this distance d can be measured directly with the help of our measuring tape. Such distance, in such case, we are going to say that our base of the object is accessible. So firstly we'll talk about this case. So as you can see here in the figure, we have our distance d. So this distance d is our horizontal distance between C and D, instrument station C and the base of the object, base of the object, we are going to name this as B dash, base of the object B dash. This distance is named as D. And we have our here we have our staff reading. Yes. So what does yes refer to? Yes refers to reading on leveling staff held vertically on benchmark with line of sight horizontal. So what we are going to do is we are going to keep a leveling staff vertically on benchmark whose RL is known, and we are going to sight it, and our line of sight is going to be horizontal. Then we are going to get certain reading on our leveling staff, and that certain staff reading is named as S. Next we have H. H is our height of instrument at C, and finally we have alpha, which is our angle of elevation for top B, and our H is our vertical height. We can name this as X. So this bx is our bx from the distance from line of sight to the top of the object. This is named as h, vertical height h. So now we already know the RL of our benchmark, and we need to find the RL of B. So in order to find the RL of B, what we are going to simply do is we are going to add RL of benchmark with staff reading S and add H to it. So in order to make the concept a little bit more clear, we have our mean sea level something over here, and up to our benchmark, this RL or this height will be known. Our RL of benchmark will be known. So we need to find our RL. In order to find the RL of B, we need to reach up to here. We need to reach from our mean sea level to up to here. We know of RL up to our benchmark. We know this much height. We know this much height. Next we know our staff reading. So we have reached over here. So if we knew the value of H, so this is remaining. If we add S to this value, we will get our RL of benchmark. So we need to firstly find the RL of we need to find this vertical height h. So in order to find our vertical height h, we'll set up our theodolite at C, and we'll calculate the vertical angle alpha. With the help of our theodolite, this value of alpha will be calculated. So next, let me jump into calculation portion. So from triangle BEX, what we have is tan alpha will be equal to bx divided by ex. So we have bx as h divided by ex as d. This d will be measured directly with the help of measuring tape. Next we have h equals to d tan alpha. So knowing the value of d and alpha, we can find the value of h. So knowing the value of h, we can simply find the RL of b as, therefore RL of B will be equal to RL of benchmark plus staff reading S plus vertical height h. So in this way RL of benchmark plus S. So let me write one more line. RL of benchmark plus S plus H is d tan alpha. So simply substitute h over here. So in this way we can find the RL of B. So our first case is solved. Now let me move on to our second case. So in our second case, our object is inclined. So over here our object was vertically upward. In our next case, our object is inclined. So as you can see here, our object AB, it is an inclined tower, and we have our distance x. Here our distance x is the distance between distance between foot of the tower and project point B dash of its top B. So we have our bottom A and top B. We have projected it vertically downward as B dash, and the distance between this point B dash, this projection of top and the bottom of the tower, this distance is named as x. Next we have C and E as instrument stations, and all these lines C, A, E and A, these three lines are in a single particular line. Now we have D1 and D2 as the distance between instrument stations C and E with the bottom of the tower, with the bottom or the foot of the tower, and we have S1 and S2 as staff reading of instrument stations C and E on the staff which is held vertically on a benchmark with the line of sight horizontal, and as in the case above, we will know the RL of benchmark. This will be known. And next we have alpha 1 and alpha 2. Both of these are the angle of elevations from C and E, respectively, to the top of this inclined tower. So this is our known quantities. Next we will be finding the RL of benchmark. So as you can see here, previously we had our instrument station at only C. Now we have instrument station at C and E. We have two instrument stations which are at the opposite sides of our inclined tower, and we have two vertical angles as well, alpha 1 and alpha 2. So for this case, what we are going to do is we are going to be using two triangles. We are going to be using this triangle first. So I am going to name this much as x. So we are going to use first the triangle BC-X. From triangle BC-X, what we have is, we had h over here, we can name bx, this much height of bx as h1. For alpha 1, vertical height is h1. Same as the case scenario of above, we have tan alpha 1 equals to bx divided by our distance down is cb dash. This will be equal to, I have named bx as vertical height h1, and for cb dash, what we have over here is ca equals to d1 and b dash a equals to x. So cb dash will be simply equal to d1 minus x. Simple, d1 minus x. So what I have over here is h1 equals to d1 minus x tan alpha 1. So I'm going to name this as equation 1. Similarly, if I use the triangle B this is E dash, okay, it is E dash, and I'm going to name this as y. If I use the triangle B E dash y, so from triangle B E dash y, what I have is tan alpha 2. It's now I have my tan alpha 2 equals to by. I haven't named by anything. I can name by as my vertical height h2. By as vertical height h2. Can do next is tan alpha 2 will be equal to by. So if you just look at this much of triangle, tan alpha 2 will be equal to by divided by eb dash. So I have named by as h2 and eb dash. So if you see eb dash is the distance from over here to here, which is equal to the sum of d2 plus x. AE is d2 and ab dash is x, so eb dash will be simply equal to d2 plus x. So what I can do next is h2 will be equal to d2 plus x tan alpha 2. So I'm going to name this as equation 2. So now let me simply calculate my RL values. So in order to calculate my RL values, so from C, RL of B will be equal to RL of B. So from C, RL of B will be equal to benchmark, RL of benchmark. I need to reach up to here. I have already reached up to here from the C level. Next I need to add S1, which is our staff reading from C, which is C S1, plus H1, which is our vertical height H1 for C H1. So this is equal to I have reached RL of benchmark plus S1. I need to reach up to here. Since I have already reached over here, I need to add the remaining H1 to reach to top. Simple as the case above. So next we'll have RL of benchmark will be equal to RL of B will be equal to RL of benchmark plus S1 plus H1. So we know the value of benchmark. We also know the value of S1 from our staff reading. This will be known. This will be known practically. And for our H1, we have H1 equals to D1 minus X tan alpha 1. Similarly, we'll find the value of we'll find the RL of B from E from our instrument station E. RL of B will be equal to, we know the RL of benchmark. We added RL of benchmark. We have reached over here we have reached up to here. For our E, we have our staff reading S2. We have already reached over here. Now we need to reach up to here. So remaining is our height H2. So add H2. So this will be equal to RL of benchmark plus S2 plus our S2 value is D2 plus X tan alpha 2. So as you can see here, the value of the RL of B will be same from both instrument station C and E. So both this value A and B, both this equation must be equal. So if you equate them, what we are going to get is RL of benchmark plus S1 plus D1 minus X tan alpha 1 equals to RL of benchmark plus S2 plus D2 plus X tan alpha 2. Both this RL gets cancelled out, so we get left with S1 plus D1 minus X tan alpha 1 equals to S2 plus D2 plus X tan alpha 2. So if we solve this equation, what we are going to get is we are going to get our value of X, which will be equal to so I am directly writing it down, S1 minus S2 plus D1 tan alpha 1 minus D2 tan alpha 2 divided by tan alpha 1 plus tan alpha 2. So we'll know our value of S1 and S2 practically, and the value of alpha 1 and alpha 2 will be known with the help of our theodolite. So and knowing the value of X, what we are going to do next is we can substitute this value of X in either of this equation A and B, and we can find the RL of our B easily. So this is our second condition for inclined object. Next we'll be moving on our next case where our base of the object is inaccessible. So now next we have our condition where the base of the object is inaccessible and instrument stations and the elevated object are in the same vertical plane. So under this also, depending upon the terrain, we have three cases. So first case is where the instrument axes are at same level. Instrument axes are at different levels but the difference in level is small. Instrument axes are at different levels but the difference in level is more. So firstly, this will be more clear when we move when we describe about them one by one. So firstly, let's talk about the first case where our instrument axes are at same level. So as you can see here, as I already talked before, we are talking about the case where our base of the object is inaccessible. So this is our base of the object. Base of the object is E, and we have our instrument stations A and B. We need to find the distance from our instrument station to the base of the object, which is our distance D. But due to certain obstacles which we have to denote over here, we cannot measure this distance D directly. In real life, this obstacle may be some river, lake, ponds, hills, or it can be anything, because of which we cannot measure this distance D directly by the help of our measuring tape. So we are going to measure this distance D also trigonometrically by the help of our with the help of our particle angles, with the help of our particle angles alpha 1 and alpha 2. So let me describe about instrument axis at same level. So what does this mean? So in order to find the RL of our object, we are going to have two instrument stations A and B, and if both these instrument stations are at same level, means the line of sight of both these station will be same, and the value of staff reading on our benchmark of both these stations will be same. They will have the both of them will have the same staff reading, yes, but they will have different angle of elevations alpha 1 and alpha 2. So as you can see here, both this A and B, they are nearly in the same nature of terrain. They are almost in the same nature of the slope, and they have the same staff reading, yes, on the staff yield vertically on our benchmark. So as you can see here, So if they have the same staff reading, so to simply say this, if they have the same staff reading on the leveling staff, we can say that the both the instruments are at same level. So as we have over here, we have alpha 1 and alpha 2. Alpha 1 and alpha 2 are angle of elevations at C from A and B respectively, and S is our staff reading on benchmark from both stations. Since they are at same level, they will have the same staff reading. And our D is our horizontal distance between staff stations A and B, and our distance D is the horizontal distance between station A and the bottom of the tower E, which cannot be measured directly, and this will be calculated trigonometrically. So as you can see here, we have two instrument stations A and B. Since we cannot measure this distance D directly, so instead we will have two angle of elevations. So now let's move on to the calculation portion. So firstly we'll be using the triangle A dash C E dash. So we need to find the RL of C. So for that we need to find the value of h, which is our vertical height, like as in previous case. So firstly what we'll be doing is we'll be using the triangle A dash C E dash. So let me use that triangle. So from triangle A dash C E dash, from triangle A dash C E dash, tan alpha 1 equals to C E dash divided by AE, or we can simply write this as h by D. So we get as h equals to D tan alpha 1. It's going to be our equation 1. Similarly, next we'll be using the triangle B dash C E dash for our instrument station B. We have from triangle B dash C E dash, tan alpha 2 equals to h by our now distance is BE, which will be equal to D plus D. So we have h equals to D plus D tan alpha 2. So this is going to be our second equation. So now what we are going to next is we are going to equate both of these equations. So equating both of this equation, we are going to have D tan alpha 1 equals to h equals to D plus D tan alpha 2. So on solving this, what we are going to get the value of D, which will be equal to D tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So as in the first part of the video, when we talked about determining our distance D trigonometrically, we meant this. We will know the value of alpha 1 and alpha 2. We'll know our distance D, small d, and knowing all these values, we can in this way we can determine the value of our D when the base of the object is inaccessible. So now what we'll be doing is we'll be using equation 1. Therefore h equals to, we have D tan alpha, so we are going to substitute this value of D over here. We are going to get D tan alpha 1 tan alpha 2 divided by tan alpha 1 minus tan alpha 2. Since we know alpha equals to sine by cos, so if we put that, we are going to get this as D equals to sine alpha 1 sine alpha 2 divided by sine alpha 1 minus alpha 2. So we can write this equation as this as well. So therefore our RL of C will be simply equal to RL of benchmark. We'll know this value. We have reached over here. We need to reach up to here. So next we'll be adding staff reading yes. So let me add that staff reading yes. So we have reached over here as well. Now our remaining height is height h. So our height s is over here. So for this case also, in this way we'll be determining our RL of C. So if you have reached till over here, and if you have understood it over here, do subscribe to the channel. It will mean the world to me, and it will help me, and it will promote me to upload more and more video. Now we'll be talking about our second case. Now we'll be talking about our second sub case. So previously we talked about the case where the instrumental axes were at same level. Now we are going to talk about the case where instrument axes are at different levels, but the difference in level is small. So as you can see here, in this case also we have two instrument stations A and B, but as you can see here, they are not at same level. the axis of our instrument, the instrumental axis is not same. As you can see here, we have our instrument A at the bottom and instrument B at the top. So as you saw in our previous case, so as you can clearly see the difference between these two cases. Previously, both of our instrument stations A and B, they were in same level, but you can see here now our instrument station B, at B the instrument is at higher ground, but at and A is at lower ground. But in this case, both A and B were at same level of ground. They were in same level of they were in same nature of terrain. So as you can see here, and they had the same staff reading yes on the benchmark. But as you can see here, instrument A has staff reading yes 1, while the instrument station B has our staff reading yes 2. So this is our second case. But in this case, the difference in level is small, which means the difference of yes1 and yes2 is quite small. They are not, it is not large. So under this case also we have two different cases. So what can be the two different cases over here is, as you can clearly see, right now we have B at higher ground, B at higher, instrumental axis at B is higher. Next case we'll have where our instrumental axis at A is higher. So we'll talk about that later. First we will talk about the case where our instrumental axis at B is higher. Instrumental axis at B is higher. So this is our second sub case. Instrumental axis at different levels, but this difference in level is small. And firstly we are going to talk about the case where our instrumental axis at B is higher. So here we have our instrument station A and B, and our S1 is our reading on our benchmark, reading on the leveling staff, held vertically on our benchmark. S1 is the reading from A and S2 is our reading from B, and alpha 1 and alpha 2 respectively are the angle of elevations to the top of our object from our instrument stations A and B, and D is our distance between the instrument station A and the bottom of the object, and this distance D cannot be calculated since the object is inaccessible, and we need to evaluate this distance D trigonometrically, and this distance D is our distance between two instrument stations A and B, and H1 and H2 our vertical height for our angle alpha 1 and angle alpha 2 for our instrument stations A and B respectively. These all are similar to our previous cases. So now firstly to determine in order to determine the RL of G, we need to determine the value of alpha 1 and alpha 2 and the value of D. So firstly what we're going to do is we are going to be using the same formula as previous. We are going to first use the triangle EA dash G for our instrument station A. So let me write it over here. From triangle EA dash G, from triangle EA dash G, from triangle EA dash G, what we have over here is we have H1, this is our height, H1 equals to no, we are going to use tan alpha 1 equals to GE divided by EA dash. So our value of GE is H1 divided by our value of EA dash is D. So we have H1 equals to D tan alpha 1. This is our first case. Next we are going to use the triangle B dash GF, or B dash GF from, this is for our instrument station B. From triangle B dash GF, what we have is tan alpha 2. Similarly what we have is tan alpha 2 will be equal to GF divided by BE. So we have GF as H2, and we have our base which is BE as D plus D. So we get H2 equals to D capital D plus small d times tan alpha 2. We have our H1 and H2. So as you can see here now, H1 from this figure, what you can observe is the difference of H1 minus H2 will be this much EF. The difference of S1 minus S2 will be this much, and this EF is equal to the difference of staff reading S1 and S2. So as you can see here, these both are equal, so EF will be equal to this much. So what we can observe from the figure is S1 minus S2 will be simply equal to S2 minus S1. So let me write it over here. From figure what we observed is H1 minus H2 equals to S2 minus S1. H1 minus S2 is equal to S2 minus S1. We are going to say this as yes. We are going to suppose this difference to be equal to yes. So now what we have over here is where we need H1 minus S2. So subtracting equation 1 and 2, what we get is d tan alpha 1 minus d plus d plus minus d plus d tan alpha 2 minus d plus d tan alpha 2 equals to, yes, we can write this, since s2 minus s1 equals to yes, so I'm directly substituting this two part. So what we get is d tan alpha minus d plus d tan alpha 2 equals to yes. So on solving this, what we're going to get is d tan alpha 1 minus d tan alpha 2 minus d tan alpha 2 equals to yes. So on taking common and moving our equations, shifting our equations left or right, what we're going to simply get is, we're going to get this as d equals to s plus d tan alpha 2 divided by tan alpha 1 minus tan alpha 2, tan alpha 1 minus tan alpha 2. So we're going to value of d. So in this case, without directly measuring the value of d, so without measuring this value of d, using our value of alpha 1, alpha 2 and d, which we can measure in measure practically, and s1 minus s2, which will also be known, we have calculate our value trigonometrically. Next, what we can do is, we can, since using the relation between tan and cot, we can write this equation as d plus s cot alpha 2 tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So we have just used the relation between tan and alpha to rewrite this equation. So next, we are going to substitute the value of d in equation 1. Now knowing this value of d, we will simply substitute the value of d in equation 1. So we have h1 equals to d tan alpha 1. So from equation 1, we have d will be equal to d plus s cot alpha 2 divided by tan alpha 2 times tan alpha 1. Our tan alpha 1 is over here, divided by tan alpha 1 minus tan alpha 2. So in this way, we'll know our value of h1, and knowing the value of h1, therefore we can substitute the equation. We can substitute the value of d in equation 2 to calculate the value of h2 as well. So we have, therefore RL of g will be simply equal to RL of benchmark plus will so in order to know h1, what we have is s1 RL of benchmark plus s1 RL of benchmark plus s1. We have reached over here, we need to reach up to here, so our remaining height is h1. We know the value of s1 from over here. So in this way, we can find our RL of g. So in this case, we had instrumental axis at B, we had B at higher ground. Next, we'll be talking about the case where A will be at higher ground and B will be at lower ground. So now, as you can see here, we're talking about the case where our instrumental axis at A is higher. So previously, as you can saw here, as you see, A was at a lower ground and B was at higher ground, but in this case we have A in a higher ground and B at lower ground. So the staff reading of A will be more than the staff reading of B. So as you can see here, the difference of in both these cases, this case B at higher, this case B is at lower and A is at higher ground. So as in the case scenario, everything is same. We have alpha 1 and alpha 2 as angle of elevations from instrument stations A and B to the top of our object, and S1 and S2 are our respective vertical component. We have our distance d from our instrument station D to the bottom of the object, and our small d is our distance between A and B, and our S1 is our staff reading for our instrument station B, and our S2 is our staff reading for our instrument station A. So like as before, we'll be using our same formula. We'll be using our triangle EA-G. So let me simply write it over here. From triangle EA-G, we have tan alpha 1 equals to GE divided by EA dash, which is equal to H1 divided by D. So we have H1 equals to D tan alpha 1. This is going to be our equation first. Next we have we are going to use the triangle GB dash F. From triangle GB dash F, we have tan alpha 2 equals to will be equal to GF divided by FB dash. Our GF value is H2 divided by our value of fb dash. Our value of fb dash will be equal to d plus d. So it is exactly similar as a previous case. So we get this as s2 equals to d plus d tan alpha 2. This is our equation second here. So like as in previous case, our difference of s1 minus s2 will be equal to our difference of s2 minus s1. So here h2 minus h1 equals to h2 minus s1, this much. ef will be equal to our sum of s2 minus s1, this much, which is equal to s2 minus s1. We are going to substitute this as s, say. So now we have from our equation 1 and 2, h2 is d plus d tan alpha 2 minus h1, which is d tan alpha 1, equals to yes. So from this again, so let me write this down directly. D will be simply equal to d tan alpha 2 minus s divided by tan alpha 1 minus tan alpha 2. So as you can see here, so this is our sub case of the case where our base of the object is inaccessible. So since we cannot measure this distance d directly, we have measured this distance d trigonometrically. So knowing the relation between tan and alpha, we can rewrite this equation as d minus s cot alpha 2 times tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So we can rewrite this equation. In this way. So next, what we are going to do is we are going to determine the RL of G. So as in previous case, we are going to substitute the value of d for h1. We have h1 equals to d tan alpha 1. So right now we know our value of d. So we can rewrite this equation as d minus s cot alpha 2 tan alpha 2 times tan alpha 1 divided by tan alpha 1 minus tan alpha 2. So now what we are going to do is, therefore RL of G will be simply equal to RL of benchmark. We have reached over here. We have our value of h1. So h1. So we need to go up to here, which is yes. So this will be equal to RL of benchmark plus s2 and h1 plus s2 plus h1. So this will be equal to so we know our value of h1 from here. So in this way, we will be calculating our value of RL of G as well. So now as you can see here, right now I got my value of D as d tan alpha 2 minus s divided by tan alpha 1 minus tan alpha 2. But in the previous case, as you can see here, I had got my value of d as s plus d tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So as you can see here, the difference is only of the sign. When the instrument axis at A is higher, I got the sign as minus s, while for the case where the instrument axis at B was higher, there is a sign of plus. So what you can do is we can write the general expression for both of these cases. So we can write this as general expression for our distance d and for distance d and height h1 can be simply written as, since there is this difference of only plus minus, we can write this as, therefore d equals to d tan alpha 2 plus minus s divided by tan alpha 1 minus tan alpha 2, or d plus minus s cot alpha 2 times tan alpha 2 divided by tan alpha 1 minus tan alpha 2. Similarly for our h as well, therefore h1 equals to, so as you can see here, I got my value of h as minus s, d minus s, while there is I got d plus s, while everything else is same, cot alpha 2, tan alpha 2, tan alpha 1, tan alpha 1 minus tan alpha 2, so same. So as you can see here, it is exactly same for the previous case as well. Therefore d will be equal to d plus minus s cot alpha 2 tan alpha 1 times tan alpha 2 divided by tan alpha 1 minus tan alpha 2, or I can write this as d plus minus s, since tan equals to sine by cos, this will be equal to sin alpha 1 sin alpha 2 divided by sin alpha 1 minus alpha 2. So I can write this equation as well. So and as a note or whatever, as a remark, what I can say is use positive sign. So when we are going to use a positive sign is, we are going to use a positive sign if station A which is nearer to the object, which is nearer to the object. So as you can see here, we have used station A as the station which is nearer to the object is lower, is lower. So as you can see here, since the instrument A was lower, we got the sign as plus. So in that case, we'll be using plus sign, and while we'll be using negative sign if the same case, if station A which is nearer to the object is higher, and this lower and higher is as compared to that of station B. So we need to understand this as well. Next we'll be talking about our third sub case where our instrument axes are at different levels, but this time the difference in level is more. Next we'll be talking about our third sub case in which our instrument axes are at different levels, but in this case the difference in level is more. So what does difference in level more mean? So as you can see here, we previously did this in this case as well. The instrument axes were at clearly different levels, but in this case the difference in level, which means the S2 minus S1, which was equal to S2 minus S1 equals to S, which we had assumed this was measurable, this was measurable, or this was not too great. This difference in value was not too great, or if I had to simply say this, the staff reading S2 from our higher level, the staff reading S2 can be easily measured with the help of our theodolite and leveling staff. But in this case, our staff reading from higher ground, which is S1, cannot be measured easily. This S1 cannot be taken easily since it is out of range of our leveling staff. This will be our out of range of our leveling staff. This S1 value will be quite great, so that the difference S1 minus S2, which is equal to S2, will also be too great. So in this case, we will have to adopt other measures to determine this value of S1. So let me describe this figure. So what we are going to do simply in our practical is, in order to determine this top of our object G, firstly we are going to set up our instrument at A, and as this is the height of our instrument at A, and firstly we are going to measure this first angle of elevation alpha 1 to the top of our tower. Next we are going to transit our theodolite and take it to our next instrument station D, which is at a distance D far away from our initial instrument station, and we are going to measure this angle alpha 2 again to the top of our tower, and we have our distance D from our instrument station A to the base of our object, and this distance D is still inaccessible, since this is our major case in which our object is inaccessible, and we are going to measure this distance d trigonometrically as well. This distance D cannot be measured directly with the help of our measuring tape. And next we have our instrument reading S2. This can be easily taken since it will be in the range of our leveling staff. So now what we are going to do is, we have to determine this value S1. Since we can determine this value S1 directly by looking in our leveling staff, so we are going to add up other measure. So what we are going to simply do is, we are going to keep a target staff of height R. We are going to keep a target staff of height R at instrument station A. At this instrument station A, we are going to keep a target staff of height R, and from our instrument station B, we are going to sight at the top of our target staff, and we are going to have our angle of elevation as alpha. After having our angle of elevation alpha, so this is A, and this is our distance h from our instrument axis to the top of our target staff, and our difference and as you can see here, our height of station A above axis at B, this is equal to h minus R. So let me write it down over here. Height of station A above axis at B. So we are going to calculate our S1 in other ways, so that we can determine our top of the tower. So we are going to add up other measures. So what I'm going to write over here is height of station A above axis at B, which means this much distance over here, or height of station A above axis at B, this much distance. Height of station A above axis at B, this is equal to h minus R. So we have h minus R, height of distance A, h minus R, and if we use formula of tan alpha, what we're going to get is tan alpha equals to p. P is our h divided by our base is d, so we're going to get h equals to d tan alpha. So as we did before, h equals to d tan alpha. So our height of station A of axis at B, which is equal to h minus r, we have h as d tan alpha, so we are going to write that we have h equals to d tan alpha minus r. So our height of station A of axis at B is d tan alpha minus r. Next, what we're going to write is height of therefore height of axis at A above axis at B. So what does this mean is we need to find the height of axis at A above axis at B, which means we are going to find the difference of s2 minus s1 or s1 minus s2 or simply s. We can write this as yes. This is equal to yes. This will be equal to s2 minus h1. Will be equal to s2 minus h1, and this will be simply equal to, therefore yes equals to now as you can see here we have our instrument. We are going to calculate yes. So this is our yes. We have this much the height as s dash, which is our height of instrument at A, s dash, plus the remaining distance is this much distance, which is our distance. This much distance we have calculated it as d tan alpha minus r. So hope you have understood this much portion. Therefore yes equals to d tan alpha minus r plus s dash. So let me explain this much portion once again. So firstly we calculate the height of station A above axis at B. This much distance, this height of station A above axis at B, this small distance which we had to calculate, which we needed to find this yes. We found this by keeping our target staff, and we calculate this to be d tan alpha minus r. This much distance from our base of our station A to the axis of B. This small distance was found to be d tan alpha minus r by using our target staff, and the remaining distance, which is our h dash, if we which is our height of instrument at A, instrument height at A. So if we add h dash and this small distance, which we find to be d tan alpha minus r, we found it equal to be our yes, which is our difference in level s1 minus s2. So previously we used to find we used to have our value of s1 and s2, and we could easily find our value of s1 minus s2 directly. But in this case, since we cannot measure this value of s1, we are going to calculate our s in this way, d tan alpha minus r plus h dash. So hope you understood this portion. Next, so what I can write over here is s dash is our height of instrument at A. So next what we are going to do is we are going to have everything as previous. So our inaccessible distance d will be simply equal to d tan alpha 2 minus s divided by tan alpha 1 minus tan alpha 2. So as we calculated before for our previous case, in which our instrument axis at A is higher, we are going to use the same formula, d minus s cot alpha 2, d tan alpha 2 minus s. We are going to use this same formula over here because both of these cases are exactly the same, so we don't need to change anything. So we are going to simply use the same formula, d tan alpha 2 minus s tan alpha 1 minus tan alpha 2, or this is equal to d minus s cot alpha 2 tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So instead of yes, we are going to place this value d tan alpha minus r plus h dash, and we are going to have our height h1 as will be simply equal to d minus s cot alpha 2 tan alpha 1 divided by tan alpha 1 minus tan alpha 2. So we have already calculated this before, so we have used the same formula for h1 as well. In the previous one, we had calculated our value of h1 as d minus s cot alpha 2 tan alpha 1, where we have used the same formula with no any changes. So we can write this equation as d minus s cot alpha 2 sin alpha 1 sin alpha 2 divided by sin alpha 1 minus alpha 2. Now we have our inaccessible distance d as well, we have our height h1 as well. Therefore in order to find the RL of top of our object, RL of G. What we're going to do is we are going to add RL of our benchmark, RL of benchmark, plus we know the value of S2 since it is in the range of our leveling staff, plus S2, plus we need our remaining. So I have reached over here RL of benchmark, plus I have added S2, so I have reached over here. So in order to reach up to here, next what I need to add is I need to add S, then H1, plus S plus H1. So as in our previous case, we have done this simply the same. RL of benchmark plus S2 plus S, so remaining height is H1. RL of benchmark plus S2 plus S plus H1. So if you had any confusion regarding this portion, how D10 alpha minus R plus S dash is calculated, you can comment down below. I will try to answer them much more clearly over there. Next we'll be talking about our final case. So firstly we talked about our case where the base of our object was accessible. Next we talk about the case where our base of the object was inaccessible, but in all those cases our instrument stations and elevated object were in a same plane. But in this case but in our final case our base of the object is inaccessible, which means we cannot measure it directly, and our instrument stations and elevated object are also not in the same vertical plane. So as you can see here, we have our instrument stations B and A, but our elevated object C, they are not in our same vertical plane, they are in our different planes. As you can see here, they are in our different level of vertical plane. So how are we going to find our RL of C, our RL of our object in this case? So let me describe through our figure firstly. So firstly what we are going to do is we have our benchmark over here, and we have our two instrument stations A and B, and we have our object C. We need to find the RL of top of our object C. So firstly let me talk about our instrument station A. So firstly we are going to set up our instrument station, set up our theodolite at station A. Firstly we set up our theodolite at station A, and we center it, and we measure our first horizontal angle BAC dash, and we have named it as beta. So let me write it over here. We have our first horizontal angle BAC dash equals to beta. So we have our first horizontal angle. Next what we do is we sight at the top of our station C. Next we sight at the top of our object C, and we observe the angle of elevation to be alpha 1. Next what we do is we set our vertical angle to 0, and we take our staff reading at benchmark, which is our S1 for A. We have our angle of elevation alpha and staff reading S1 for A. Next what we do is we shift our theodolite to station B, and we center it over there, and we observe our horizontal angle C dash BA, which is our alpha. We shift our instrument to B, and we observe our horizontal angle C dash BA, which is equal to alpha using our theodolite. So C dash BA equals to alpha, angle C dash BA equals to alpha. This both this alpha and beta will be measured with the help of our theodolite. So next what to do is from our instrument station B also we sight at the top of our object. We sight at the top of our object, and we observe our angle of elevation to be alpha 2, and what we do is we set our vertical angle to 0. We set our vertical angle to 0 and take staff reading at benchmark, which is equal to S2. Next we measure our horizontal distance between two instrument stations A and B, and it is found to be A and B equals to distance AB equals to D. So we have our angle alpha and angle beta, both are calculated with the help of our theodolite, and we have our staff reading S1 and S2 from our respective instrument stations A and B, and we have our angle of elevations alpha 1 and alpha 2 from our instrument station A and B to the top of our object C. So next what we do is now we are going to and we have measured this horizontal distance D as well. Now next what we are going to do is we are going to use the horizontal triangle ABC dash. So let me write it over here. In horizontal triangle ABC dash, so we are going to use the horizontal triangle ABC dash. We have our angle alpha and our angle beta. So our angle AC dash B. So our angle AC dash B equals to 180 degree minus alpha plus beta, and we are going to name this angle AC dash B as theta. Next what we are going to do is we are going to use our sine law in our triangle ABC dash. So why are we going to use our sine law is we need to find our value AC dash, and we need to find our value BC dash in order to use our tan alpha and tan alpha 2 like in previous cases to determine our value S1 and S2. So next what we are going to do is we are going to applying sine law, applying sine law in triangle ABC dash. Applying sine law, we have AC dash divided by sine alpha, opposite angle alpha, equals to BC dash divided by sine beta, BC dash divided by sine beta equals to our we have our remaining AB divided by sine theta, AB divided by sine theta. So right now we know the value of AB, which is equal to D. Next what we're going to do is we have AC dash equals to D sine alpha divided by sine theta, divided by sine theta. This is equal to sine alpha divided by, we have our value of sine theta as sine 180 degree minus alpha plus beta. So we have d sine alpha divided by, since sine 180 degree minus theta equals to sine theta, so we're going to simply write this as sine alpha plus beta. Next we are going to write the value of bc dash. So using these two equations, bc dash will be equal to d sine beta divided by sine theta. So following this same step, we can write sine d sine beta will be equal to sine 180 minus alpha plus theta, which will be finally equal to sine alpha plus beta. So we'll know our distance d, we'll know our angle sine beta, we'll know the value of alpha and beta from with the help of our theodolite, and we can calculate our distance AC dash and BC dash. So now knowing this value, we are going to use the formula of tan alpha 1. So we have our tan alpha 1 will be equal to h1 divided by AC dash, So our h1 will be simply equal to AC dash tan alpha 1, So in this way we can find the value of h1. So our AC dash value is over here, which is d sine alpha divided by sine alpha plus beta times tan alpha 1. Similarly, we will calculate our value of tan alpha 2. Tan alpha 2 will be equal to h2 divided by b dash, h2 divided by bc dash, h2 divided by bc dash. So our value of h2 will be simply equal to bc dash tan alpha 2. We have our value of bc dash as d sine beta divided by sine alpha plus beta times tan alpha 2. So now we know our value of h1 and h2. Now knowing the value of h1 and h2, we are going to find our RL of C, RL of our top of our object. Therefore finally RL of C will be simply equal to RL of benchmark. Firstly, RL of benchmark plus, if we are going to use S1, we are going to use our height h1, RL of benchmark plus S1 plus our remaining height is h1 plus h1, which will be simply equal to RL of benchmark plus S1 plus our h1 value is this much, d sine alpha divided by sine alpha plus beta times tan alpha 1. Similarly, our RL of C can also be calculated using our value of alpha 2 and S2. So we have RL of C equals to RL of benchmark plus, I am going to add height S2 plus our remaining height will be H2 plus H2. So will be equal to RL of benchmark plus S2 plus S2 value is d sine beta divided by sine alpha plus beta times tan alpha 2. So you might have some confusion regarding how S1 and S1 will add to this. So we have so what we have in a real is we are going to have some, these are all going to be connected in such a way. We are going to have some different elevations of particle plane, and they are going to be in different particle plane. And if I had to simply say, what I have is, I have reached over here RL of benchmark, and this much height will be equal to this much height. So this will be S1, this will be our simply S1. These two are going to be equal, and remaining height is going to be H1. So I can draw my parallel lines in this way as well. in this as well, so they are going to be simply equal. And similarly for my s2 as well, I'm going to have this much remaining height as s2. So we'll have our RL of benchmark over here, then we'll be continuing it up to s2 and h2. So in our 3D this figure might look a bit confusing, but our RL of C will be simply equal to our RL of benchmark, staff reading from our theodolite and the respective vertical height. So we are going to next solve our 5 different numericals based on our different cases to make the concept even more clearer. So now we have our first question. We need to draw figures of our each and every question, so that we can easily evaluate how our setup is, which case we are talking about, and we can easily solve our question. So let me now read the question. We have our question as: an instrument was set up at A. An angle of elevation of top of an electric pole BC was 24 degree 36 minutes. The horizontal distance between A and B, which is our foot of the pole, was 600 meter. Determine the RL of top of the pole if staff reading held on benchmark whose RL is 100 meter. RL of 100 meter was 2.532 meter with telescope in horizontal plane. So we have our sum. So let me write down solution. We have our sum given. An instrument was set up at A, an angle of elevation of top of electric pole BC, which means we have our angle of elevation given over here, our angle of elevation. So I'm going to write this as angle of elevation given. Angle of elevation alpha equals to 24 degree 36 minutes. Next we have the horizontal distance between A and B, the foot of the pole, was 600 meter. So as you can see here, we have measured our horizontal distance between our instrument station, which is A, and the foot of our tower, which means we are talking about our case when our base of the object is accessible. So right now we are talking about this case where our first case where our base of the object is accessible. So we have our this formula, but we're not going to memorize any formula. We are going to use our figure and solve our numerical. So this is our first case where our base of the object is accessible, and regarding vertical or inclined object, we haven't been given our object as inclined in the question. As you can see here, there is no any word inclined, so we are going to say our object is vertical. We have our vertical object, so we need to draw our figure in this way for our first question. So our base is accessible and our object is vertical. So firstly, let me write down the given, the horizontal distance between A and B. So our horizontal distance between A and B, so I'm going to name this as horizontal distance, which is our capital D, will be equal to 600 meter. And we have our determine the RL of the top of the pole if the staff reading, so I'm going to write this as staff reading. I'm going to note my staff reading as small s, so it will be equal to 2.532 meter. Our RL of benchmark is 100 meter, so our RL of benchmark equals to 100 meter. So I need to draw the figure, so I'm going to draw my figure in this way. So we have our figure as this way. So firstly we have our instrument station A, so let me draw that instrument station A. This is my instrument station A. Next we have our top of electric pole BC, our top of electric pole B, and this is my foot of the pole B, and my top of the pole is C. And I'm going to draw my instrument axis, and I have my benchmark over here, and my RL of benchmark is 100 meter. RL of benchmark is 100 meter, and this distance between A and B, this is my capital D, is equal to 600 meters. So I'm going to, and now this is I'm going to see it over here, and this is going to go over here, and if I simply do this is going to be my angle of elevation. So I've drawn my figure. Roughly this angle of elevation is equal to 24 degree 36 minutes. This is equal to alpha. And next we have this much my staff reading, which is equal to 2.532 meter. 2.532 meter. So this is going to be my figure for our first question. So you must so drawing the figure is very important part, unless and until you learn how to draw a figure, you are not going to be able to solve your questions. So next what we are going to do is, so next I have named this much as B dash straight to our instrument axis, our horizontal axis, and I'm going to name this much distance B dash C as our vertical height H. So So you must know why we are going to name this, because our RL of C will be equal to RL of benchmark plus staff reading, which is up to here, and the remaining height is h b dash c. We need to find our value of h. So this is our, I'm going to name this as a dash. This is our very simple question. So we are going to use our triangle a dash c b dash. So let me write over here, from triangle a dash c b dash we have tan alpha equals to h by d. Now I have my tan alpha is 24 degree 36 minutes equals to h, which is b dash c, divided by d is 600 meters. So therefore my value of h will be equal to 600 into 24 degree 36 minutes, which will be equal to 274.70 meters. 274.70 meter. Next I need my RL of top of the pole, which is RL of C. So let me write over here. Therefore RL of the top of the pole, it will be equal to RL of benchmark, I is up to here, RL of benchmark plus my staff reading plus my vertical height, which is b dash c, is equal to h. Determine my RL of top of the pole. I have my RL of benchmark, I is up to here. I have my staff reading s, which is 2.532 meter, and my remaining height is b dash c, which is equal to h. So I can write b dash c over here. So I have RL of benchmark, which is given in my question as 100 meters, staff reading s, which is also given in question 2.532 meter, plus my b dash c, which is equal to h, is equal to 274.70 meter, and this will be equal to 377.23 meters. So therefore my RL of top of the pole, RL or the RL of C, will be equal to 377.23 meters. So in this way you can solve your first question. Next we'll be solving our problem number 2. So now let's talk about our problem 2. So the question is quite long, so let me read the question. To determine the RL of top of television tower, so we need to determine the RL of top of the television tower surrounded by transmission buildings and other administrative blocks. A theodolite was set up at A in an adjoining park, and an angle of elevation alpha 1 was measured and found to be 33 degrees 70 minutes. So from this much reading, so what I can write is, so let me write my given right over here. So firstly what I know is I need to determine the RL of top of television tower, and I have my first instrument station at A, and the angle of elevation. From this I have calculated my angle of elevation to the top of the tower, and this angle of elevation alpha 1 was found to be 33 degrees 70 minutes. So let me write over here angle of, so let me write it from A angle of elevation from A, angle of elevation alpha 1 equals to 33 degree, angle of elevation alpha 1 equals to 33 degrees 70 minutes. So instead of reading the whole question, just read certain portion of the question and write whatever is given. It will be easier for you. The reading on a staff held on benchmark with telescope in horizontal plane was 1.58 meter. So with the instrument station at A only, we backside in our benchmark on the staff held on benchmark, and the reading, the staff reading S1 was found to be 1.585 meters. This is for our instrument station A only. So let me write down over here staff reading S1, which is S1 equals to which is equal to 1.585 meter. Next what we do is the theodolite was translated and another point 100 meter away was fixed. Okay, so now we have our another instrument station B. So let me write over here, from B we have our distance between A and B as 100 meter. So let me write that over here. Let me write it over on top only. Distance between A and B equals to 100 meters. The angle of elevation of top was measured at B and found to be 26 degree 24 minutes. So we have angle of elevation from B on the same top of the tower alpha 2 was found to be 26 degree 24 minutes. Okay, the reading on staff held on benchmark was again 1.58 meter. So from our instrument station B also we found our staff reading, which is equal to S1. Staff reading S2 equals to 1.585 meter. If the RL of benchmark is 294.819, find the RL of top of television tower. So let me write my final data given. RL of benchmark equals to 294.819 meter. So reading up to here, what we can find is, what we know is, we have our two instrument stations A and B, and they are 100 meter apart, and the angle of elevation from A to the top of the tower is 33 degree 33 degrees 70 minutes, and the staff reading is 1.585 meter. And from B we have our angle of elevation as 26 degree 24 minutes, and we have our same staff reading, which means since we have our same staff reading, what we can conclude is both we can conclude is the instrument stations A and B, they are at same level. So they are at same level, and since we haven't been given the distance from our instrument station to the base of our tower, what we can say is our base of the object is inaccessible. It has been given over here, surrounded by transmission buildings and other administrative blocks, which mean that we cannot reach the base of the object or the base of this tower, which means we have our distance d as inaccessible. So let me draw my figures. This is my second case. So right now we are talking about this case where our base of the object is inaccessible due to some obstruction, but we have two angle of elevations, alpha 1, alpha 2, and we have our same staff reading, yes, these instrument stations A and B are in same level. So this is our figure. So this is our figure for question number 2. But what question might arise in our mind is, will instrument station A be which instrument station A or B will be in the forward? So as you can see over here, this will be determined by our angle of elevation alpha 1. Whichever angle of elevation is more, we are going to draw that station nearer to our object. So as you can see here in this figure, we have drawn our object A, we have drawn our instrument station A nearer to the object. This is because our angle of elevation alpha 1 is greater than our angle of elevation alpha 2. So in this figure also we have our angle of elevation alpha 1 for instrument station A greater. So our instrument station A is going to be closer to our object than instrument station B, and they have same staff reading. So both the instrument stations are in same level. So now let me draw the figure. So now we draw our figure in this way. So we have our station A closer to our tower. So let me draw this way. So what we are going to do first is we are going to draw our object. We are going to draw our tower, television tower. We have to which is our object. So let me draw my television tower over here. So my television tower, I'm going to draw it in this way. Television tower. This is going to be my television tower. This is going to be my television tower, and you can draw it in this way. So this is my television tower. So another point B, this is my B, and as you can it is not given any for the top, so I'm going to name this as C. So I have my instrument setup A and instrument setup B. So my instrument, so as I already explained before, since my angle of elevation is greater for A, since alpha 1 is greater than alpha 2, the instrument station A, this instrument station A is going to be closer to our tower. And next I have my instrument station B. And they both have the same, and they have the same level, same instrument axis, and this is known from the fact that they have the same staff reading, 1.585 meters. So I'm going to have my benchmark over here. So this is going to be my benchmark. This is my benchmark, and I'm going to have my same staff reading. My staff reading is 1.585 meter. So I can name this much as I can name this as a yes1, or yes, we can name anything. I'm going to name this as a yes equals to 1.585 meter, 1.585 meter, and this is my instrument station B. And what we have been given is the angle of elevation alpha 1, which is from over here. This is equal to alpha 1, and this is equal to alpha 1, and this is equal to alpha 2. So I have my alpha 1 as, I'm going to name this as A dash, this as B dash, and now I have my alpha 1 as 33 degrees 17 minutes, and I have my alpha 2, this is alpha 1, and this is my alpha 2 from station B, which is 26 degree 24 minutes. So I'm going to write it this way. And now I have my distance between A and B, which is small d. So let me write it directly. Small d from A to B is equal to 100 meters, while the distance from instrument station A to B is unknown. So I'm going to name this as D, and I'm going to name my vertical height from over here, from vertical height from here till here as H. this is going to be h. So I'm going to name my vertical height as h. So in order to find my RL of C, I need to find my RL of H as well. So that is the important part. So now in order to find out RL of top of television tower, so what we are going to do first is we are going to use, so I'm going to name this much as X. So firstly we are going to use first triangle. We are going to use the triangle A dash XC. So let me use this triangle. From triangle A dash XC, what I have is 10, 33 degrees 17 minutes equals to H upon D. Similarly, using this triangle B dash CX, from triangle B dash XC, so using this triangle now I have 10, 26 degree 24 minutes equals to, perpendicular is again H divided by 100 plus D. So from both this equation what I get is H equals to 10, 33 degree 17 minutes into D, and from this equation I am going to get H equals to 10, 26 degree 24 minutes into 100 plus D. Since both of these H have same values, so if I equate this equation I am going to get 10, 33 degree 17 minutes into D equals to 10, 26 degree 24 minutes into 100 plus D. So if I solve this I am going to get the value of D, which is equal to, D will be equal to so D will be equal to 310.56 meter, 560 meter. So I am doing this directly. You can solve this and you'll be getting the same value. So the distance between instrument station A and the base of the object B, this D is equal to 310.56 meter. So substituting this equation over here, I'm going to name this as equation 1, this is equation 2. So equating equation 1 and 2, I got the value of D. Now if I substitute the value of D in equation 1, I'm going to get my value of H, which is equal to 10, 33 degree 17 minutes into 310.560, which is simply equals to 203.87 meter. 203.87 meter. So now knowing the value of H, I can calculate my RL of top of television tower, RL of top of television tower, which is RL of C. Therefore, I am going to write simply as RL of top of television tower equals to RL of benchmark over here, RL of benchmark, which is given by my question as 294.819 meter, plus RL of in RL of benchmark we are going to add the staff reading yes, so just writing staff reading yes plus vertical height H, which will be equal to RL of benchmark is given by my question as 294.819 meter plus staff reading yes is 1.585 meter plus my vertical height H, which is calculated is 203.87 meter. So adding all these three quantities I get my RL of top of television tower as 500.274 meter. So for our second question we are going to calculate our RL of top television tower in this way. Next we are going to do our problem 3. So if you have till this portion of the video, do subscribe the channel. It will mean a lot to me. So now moving on to question number 3. In question number 3 we have been given our data in tabular form. So let's read the question. It says, to determine the elevation of top of the chimney, following observations were made. First we have our station P and we have reading on benchmark as 2.870, and we have station Q, and for it we have reading on benchmark as 3.750. So as you can see here we have different reading on benchmark, which means we have different staff reading S1 and S2, which means that our instrument is not at instrument axis is not same, which means our instrument axis are at different levels. As you can see over here, since the staff reading for both the station P and Q are not same, S1 is 2.870 while the S2 is 3.750, we can say that our instrument are not at our instrument axis is not same, our instrument are at different levels. While in our question number 2 both the staff readings were same, therefore we said that our instrument axis was same, but in this case our instrument axis is at different level, and we have our angle of elevation as 28 degree 42 minutes and 18 degree 6 minutes. So which means that P is going to be our nearer to the top of the chimney, nearer to the base of our object. So P is going to be, so let me write over here, P is going to be near to the base of the object. So we have cleared our first first thing. So we need to know this before drawing our figure. So this is our first requirement. And our second requirement was what we need to know is, so let me show the case. So we're right now we're talking about this case where our instrument axes are at different levels. So we found out that P is closer to our base of the object, but we also need to know that either which one is in higher ground, either A is in higher ground or B is in higher ground. So as we talked before, we had two different cases. First case we talked about where instrumental axis at B is higher, where our second case was instrumental axis at A is higher. So how are we going to know that? So how are we going to know while which instrumental axis is higher, it is of P or it is of Q? We are going to know that by seeing our reading on benchmark. So as you can see here, the reading of benchmark for P is 2.870, while for Q is 3.750. So as you can see here, according to our case, so right now P is at higher ground. The instrumental axis of of B is higher, and it has greater S2, which means staff reading of S2 is greater, while the A is at lower ground, or the instrumental axis of A is lower. It has small staff reading S1 on the benchmark. So in this way we can see here, since the P has a lower staff reading, so P has less instrumental axis or lower instrumental axis. Let me write out over here, lower instrumental axis than Q. So this so knowing these two, we can draw our figure. So we found that P is nearer to the base of the object, but P has lower instrumental axis. So now we need to draw a figure in such a way that our P is at lower ground, Q is at higher ground, and P is nearer to the object than Q. So we need to draw. So now we're going to draw a figure in this way. We're going to draw our instrument station P nearer to the object, and instrument station P is going to have a lower instrument axis at a lower ground than Q. So P is going to be closer to the object and in lower ground. So we're going to draw a figure in this way. So in this elevation, in this top portion, I'm going to draw my top of the chimney, or I'm going to draw my chimney in this way. So after drawing my chimney, I need to fix my two instrument stations P and Q. So as talked before, I'm going to place my instrument station P nearer to the base of the object. So instrument station P is going to, so let me draw my benchmark over here. Firstly, this is going to be my benchmark. I'm going to draw my instrument station P nearer to the nearer. So this is my instrument station P, and instrument station P. So let me draw my instrument axis. So this is my instrument axis, and over here, and this is going to be my alpha 1, angle of elevation alpha 1, which is 28 degree 42 minutes. So this is going to be 28 degree 42 minutes, 28 degree 42 minutes, and I'm going to have my staff reading of 2.870 meter, which is S1 equals to 2.870 meters. This is my station P. Next, I'm going to place my station Q, which is going to be at higher ground than P, and it is going to be behind of P since it has less angle of elevation. So as explained before. So let me draw my Q over here. And in this way. This is going to be my instrument axis at higher ground. This is my instrument axis at higher ground, and here is going to be my angle of elevation up to here. So my angle of elevation in this case is 18 degree 6 minutes. So let me place that as well, and I'm going to have my staff reading S2, which is this much up to here. This is S2 will be equal to 3.750 meter. So as you can see here, this figure perfectly fits the data. And now we have our let's read the question more. The top of the chimney and stations P and Q are in same vertical plane. Vertical plane PQ is 100 meters. So this distance between two instrument stations PQ is 100 meter. If the RL of benchmark is 100 meters, so RL of benchmark, this will be equal to 100 meter. Determine the elevation of top of the chimney. So we need to find this elevation of the top of the chimney. So we are going to name this as P dash, we are going to name this as Q dash, and we haven't been given any so we're going to name this as A, this as B, and this as C, and this as C dash. And we need to find this one is h1. This much is going to be h1. I'm going to name this much b to c, which is for our angle alpha 1 as h1, and for our angle alpha 2 I'm going to name this much as h2, my vertical height h2. This much height from a to c. B to c is h1, while a to c is h2. So now we are going to use the same formula as before. Now we're and I'm going to name this much distance from our instrument axis P to the base of the object as D. So now we are going to use our triangle P dash CB and Q dash CA. So let me first use my triangle P dash CB to find the value of H1. So let me use my triangle from so let me write it over there. From triangle P dash CB we get tan 28 degree 42 minutes equals to tan 28 degree 42 minutes equals to h1. Perpendicular is h1 divided by d, h1 over d. So we get so what I get is h1 equals to d into 28 degree 42 minutes. Similarly, if I use my triangle Q dash CB from triangle Q dash CB, what I get is tan 18 degree 6 minutes equals to tan 18 degree 6 minutes equals to h2 divided by my base is 100 plus d. So now my base is this much, as you can see here, 100 plus d. So from this I'm going to get h2 equals to 100 plus d times tan 18 degree 6 minutes. So we are going to use shorten relation now. So as we talked before in our proof as well, while discussing this case, while discussing our second case as well, we already discussed this. We have our s2 minus s1, which is equal to this much, is equal to h1 minus s2. So as you can see, s1 minus s2 equals to s2 minus s1. The difference of s2 minus s1 is this much, and the difference of s1 minus s2 is also this much, and both of these are equal. So we are going to use this relation. So we have our value of s2 as 3.750 minus our value of s1 is 2.870 equals to h1 is d into tan 28 degree 42 minutes minus 100 plus d into tan 18 degree 6 minutes. So we have 3.750 minus 2.870 will be equal to 0.880, and our right side of the equation will be equal to 0.22d minus 32.68, and on solving this we are going to get the value of d, which is going to be equal to 152.570 meter. So now we are going to substitute this in this equation 1. So I'm going to name this as equation 2. So from our equation 1, what we get is h1 equals to d into h1 equals to our value of d is 152.570 into tan 28 degree 42 minutes. So on this multiplication, I am going to get my value of h1 as 83.53 meter. So I have now my value of h1, I have my value of s1, and using this value I can calculate my RL of C or RL of the top of the chimney. What we can do is we can use s2 and s2 as well, but I'm going to use s1. So therefore the RL of elevation of top of chimney. So right now I'm going to use h1. So I'm going to write this as RL of benchmark plus I have reached over here. I have my remaining distance as s1 plus my remaining distance up to the top is h1. So let me write h1. Simply this is equal to RL of benchmark is given in question as 100 meters plus my value of s1 is 2.870 meter plus my value of h1 is 83.53 meter. On adding all of this, I'm going to get my RL of elevation of top of the chimney as 86.4 meter. So in this way we are going to solve this question number 3. Next we are going to solve question number 4. So now in our question we have been given as find the RL of a spire C from the following observations taken from two stations A and B, which are 50 meter apart, which means the distance between two instrument station A and B is 50 meter, and angle BAC 60 degree, angle ABC 50 degree, angle of elevation from A to top spire 30 degree, angle of elevation from B to top spire 29 degree, staff reading from A on benchmark of RL 20 meter. The benchmark has RL 20 meter is 2.5 meter, and staff reading from B to same benchmark is 0.5 meter. So as you can see here, we have been given angle BAC and angle ABC. This means that we are talking about such a case when our instrument axis are at different levels. Instead we are talking about the case where our base of the object is inaccessible, and our instrument stations and our elevated object are not in the same vertical plane. So as you can see here, we haven't been given any distance or to the base of the object, so our base of the object is definitely inaccessible, and we need to calculate it trigonometrically. And as we have been given angle BAC and angle ABC, so we can ABC, and we have been given different elevations and different staff readings. From all this we can come up to the conclusion that we are talking about the case, we are talking about this case, we are talking about the case where our base of the object is inaccessible and instrument stations and elevated object are not in the same vertical plane. So before jumping into this numerical, you must properly know this concept. So in order to know this concept properly, check the link in the description box. So right now what we're going to do is, now we are draw the figure exactly like this, equivalent to this figure. And in order to draw this figure, there might be a certain confusion regarding so we have our benchmark over here, we have our object, over here, which is our top of the object, whose RL we need to determine, and we have our two instrument stations A and B. So what might be a confusion over here is whether we are going to draw instrument A downward or instrument B downward, or either we are going to draw instrument B upward or instrument A upward. So that might be a confusion, and in order to clear that confusion, what we can simply see from the figure is the staff reading from B is S2 and staff reading from A is S1, and the staff reading from B S2 is greater than staff reading from S1. So as in our problem before, so as in our problem number 3, what we can simply come to the conclusion is that higher the staff reading, higher is the elevation of our object. Higher the staff reading, higher is the elevation. So as you can see here, in this case S2 is greater than S1, so B is instrument station B is upward than in instrument station A. So in this question as well, as you can see here, we have our staff reading from A on benchmark of RL 20 meter is 2.5 meters. Staff reading from A is 2.5 meter, while the staff reading from B to same benchmark is 0.5 meter, which means instrument station B is going to be downward and instrument station A is going to be upward. So let me draw the figure for this question. So as I explained before, we are going to have 4 different points in different vertical planes which are not in same vertical plane. So firstly I'm going to have my benchmark over here. This is going to be my benchmark. Next what I'm going to have is, I'm going to have my two instrument stations. This is going to be my instrument station first, and this is going to be my instrument station second. So as I explained before, B has lower staff reading, so B is going to be in lower elevation and A is going to be in higher elevation. And finally I'm going to draw my object over here. This is going to be my object. I'm going to name this as C, RL of such spire. This is already given in my question. So now in order to complete my figure, what I'm going to do next is, let me draw a leveling staff over here. So firstly I'm going to draw for my instrument station B. So what I'm going to do is, I'm going to place my instrument over here, and now from our instrument station B we are going to draw till the top of the tower. So we can draw this in this way. So what we are going to do next is, we are going to, so let me mark in this way. So we're going to draw in this way. So let me draw this little bit tall, and this is going to be our till top. And my angle is given as, from my question I have been given angle of elevation from B to the top spire is 29 degree. This is my 29 degree, and I need to have a backside on my benchmark, and backside it on my benchmark, and this much is equal to I have been given my staff reading from B to same benchmark is 0.50 meters. So I'm going to name this much as S1. This is equal to 0.5 meter, and I'm going to shift to my instrument station A. I'm going to do the same as well for this instrument station. What I'm going to do is, let me draw my line of sight this way. I'm going to have my angle of elevation to the top of the tower. I'm going to name this as C. I can name this as C dash. Let me name this as C dash, and let me name this as X, and this much as Y, and this much C dash Y will be simply equal to H1. I'm going to name this much as H1, and this much C dash till X, this much will be equal to H2. So I'm going to name this as H1, and this much as H2, and I have my, I'm going to name this as A dash, and I have been given from my question that angle of elevation from A to top spire is 30 degree. From angle of elevation from A to top spire is 30 degree. So in this same manner, I'm going to backside on my instrument station, and this much height S2, this much height S2 is given as 2.50 meter from my question, 2.5 meters. So in this way. So now I have drawn my figure pretty much, and what I can do is I can draw this as well. So this much will be basically so this much will be basically equal to my staff reading. This much will be basically equal to my it will be basically equal to my staff reading. So I can draw in this manner. I can draw another parallel line. So this much will be equal to my staff reading S1. So my RL of C will be simply equal to staff reading S1 plus H1. So simply in this way I can calculate my RL C dash. Similarly for my A as well. So let me draw few more lines. Let me join this line, and from my base of the A till over here as well I need to draw another line. So these are my horizontal angles which are calculated by the help of theodolite, and this is given in my question as well. My angle BAC equals 60 degree. This angle will be calculated practically in the field with the help of our theodolite, and we have our angle ABC as 50 degree. So this much angle equals to 50 degree. I'm going to name this much as B dash. So next what we are going to do is we have also been given that from two stations A and B 50 meter apart. So what this means is our distance A till B, this much distance equals to 50 meter. Next we are going to use various properties of triangles and sine law to determine our value of AC and BC, to finally determine H1 and H2 to calculate our RL of C dash. So now what we are going to do next is we are going to use our horizontal triangle ABC from our horizontal triangle. So let me simply write this in horizontal triangle ABC. What we have is angle ACB. Angle ACB will be simply equal to 180 degree. Angle ACB will be equal to 180 degree minus 60 degree plus 50 degree. This will be equal to this will be simply equal to 70 degree. 70 degree. So we have this angle as 70 degree. Next we are going to use sine law in this triangle to determine AC and BC. When we determine AC and BC, we will be able to use them to calculate H1 and H2 respectively. So next what we are going to do is we are going to use sine law in triangle ABC using sine law in triangle ABC. What we have is we have sine 60 degree divided by BC sine. So let me write in this way. AB divided by opposite angle sine 70. AB divided by sine 70 degree will be equal to AB. We have BC divided by sine 60 degree. BC divided by sine 60 degree will be equal to CA divided by sine 50 degree. CA divided by sine 50 degree. Now by the question I have been given my distance AB as 50 meter. So now what we are going to do is we have my AB as 50. So let me write it over here. 50 divided by sine 70 equals to BC divided by sine 60 equals to CA divided by sine 50. CA divided by sine 50. What we have next is we are going to use this two first relation to find the value of BC, which will be equal to BC equals to 50 into sine 60. 50 into sine 60 divided by sine 70 degree. This will be equal to 46.08 meter. So my value of BC is this much. Similarly for my CA, I am going to use first and third equation. So I get my value of CA as 50 into sine 50 divided by sine 70 degree, and this will be equal to CA will be equal to 40.76 meter. So next, knowing this value, we are going to use triangle A dash C dash CX, and we are going to use next triangle B dash C dash Y. So let me firstly use my triangle B dash C dash Y. So from triangle B dash C dash Y, what I simply have is tan 29 degree equals to h1 divided by B dash Y, and this B dash Y is equal and parallel to BC. We have B dash Y, or I can simply write this as BC. BC equals to B dash Y. So let me write one more line. This is equal. B dash Y and BC are equal and parallel to each other. So I have tan 29 degree equals to h1 divided by BC. BC equals to B dash Y, which is equal to I have calculated my BC as 46.08 meter. Therefore my h1 will be equal to 29 degree into 46.08, which is simply equal to 25.54 meter. So this is my h1. Next I'm going to use my triangle from triangle A dash C dash X. Similarly, from A dash C dash X, what I have is tan 30 degree equals to h2 divided by AX, and this AX is equal and parallel to AC divided by AC, which is equal and parallel to A dash X. So I have my tan 30 degree as h2 divided by my AC value or CA, whatever this is equal to 40.76 meters. Therefore h2 will be simply equal to tan 30 into 40.76, which is equal to 23.53 meter. So I have calculated my value of h1 and h2, and using this value we are going to find our RL of top spire, which we are going to find the RL of this top. And how we are going to find it? We are simply going to use this formula we have. So let me write this from A. So right now I am going to use my data from instrument station A. So instrument station A and from B. So let me explain it this way. So what we have is from our B, as I already explained before, I have my RL of benchmark. If I add S1 staff intercept S1, this staff intercept S1 will be equal till over here. So S1 will be equal to over here, and if I add S1, remaining S1, I'm going to get my RL of top of the top spire, or RL of the top. So therefore from B, let me write it over here, RL of top spire will be simply equal to RL of benchmark plus staff reading from B, which is S1, which is equal to 0.5 meter staff reading S1, plus I'm going to write the height h1, this height h1, which we calculated already. We have our RL of benchmark as 20 meter, and we have our 0.5 meter staff reading S1, and we have our S1 as 25.54, and on adding this we are going to get the value 46.04 meter. Similarly from our A as well, RL of top spire, similarly as that of B, our RL of top spire from A will be equal to RL of benchmark. In the RL of benchmark, we are going to write the staff reading from A, which is equal to 2.5 meter plus our value of h2. So we are going to write in this way, RL of benchmark is 20 meter plus 2.5 meter plus h2 is 23.53 meter, and on addition of this we are going to get the value as 46.03 meter. So as you can see here, we got a little bit of difference, 0.03, 0.04. So when we get so therefore our RL of top spire will be simply equal to, we are going to take the average of both these values. So RL of top spire will be equal to 46.03 plus 46.04 divided by 2, which is equal to 46.035 meter. So in our question we have been given as the top Q of a chimney was sighted from two stations P and R at very different levels. The stations P and R being in line with the top of the chimney. The angle of elevation from R to top of the chimney was 38 degree 21 minutes, and that from R to top of the chimney was 21 degree 18 minutes. So what we understand from up to this sentence is that we have two instrument stations P and R, and the angle of elevation from instrument station P to the top of the chimney was 38 degree 21 minutes, and the angle of elevation from instrument station R to top of the chimney was 21 degree 18 minutes, which means that here the angle of elevation from P to top of the chimney is greater than that of R to the top, from R to the top of the chimney, which means instrument station P is closer to our closer to the base of the chimney. We have already discussed about this in earlier. Next what we have is the angle of elevation from R to a pane 2 meter above the foot of the staff held at P was 15 degree 11 minutes. So with our instrument station at R, we have kept a pane of height 2 meter at station P, and that angle of elevation from R to that staff held at P was found to be 15 degree 11 minutes. Next what we have is the height of instrument at P and R were 1.87 and 1.6 meter respectively. The original distance between P and R, which means the original distance between two instrument stations, is 127 meter, and RL of R was 112.78 meter. Okay, we have been given RL of instrument station R. Find the RL of top of the chimney and original distance from P to the chimney. So looking at all this and being given that a vane has been placed at instrument station P, we are talking about the case where our instrument stations are we are talking about the case where our instrument stations are at different levels, but in this condition the difference in level is much more higher. The difference in level is high since difference in level is high since we have since our question says that we have kept a vane of height 2 meter at staff at station P. So right now in this question we are talking about this case. We have our two stations, and in order to find our staff reading, we keep our target staff, or in our question we have been set a vane at one of the stations, and we sight it from our other stations, and we have our angle of elevations, and we calculate our R and H and D respectively. So D has been given, we calculate our R. H has also been given in our question, which is of 2 meter. R has been given in our question as 2 meter, and we need to calculate H. So let me draw the figure for this question, then it will be more clear. So what we have over here is we have our two instrument stations. So let me draw my figure this way. We need to draw two figures. So let me draw my first figure firstly. So I have my chimney over here. This is in this way. Next what I have over here is, next I have my two instrument stations P and R, and I already explained before the instrument station which has a greater angle of elevation will be nearer to our object. So I'm going to name this as Q, the top Q. This is given as top Q. So what I'm going to do is I'm going to place my instrument station P over here. Instrument station P will be closer, and instrument station R over here, which is little bit downward since it has less angle of elevation. So let me place my instrument station R over here firstly. So in this way. So let me draw it downward. Next I am going to draw my length from here to here. So next I have my instrument station P over here. So let me draw my instrument station P in this way, and so I have my staff reading this way, and I need to draw up to here in this way. So I have been given this as P dash, this will be equal to R dash, and I have my angle of elevation. So let me write down my angle of elevation from P to top of chimney is 38 degree 21 minutes, while from R is 21 degree 18 minutes. Similarly, let me write everything given. My height of instrument at P is P and R. P is 1.87 meter, while that of R is instrument height is given as 1.64 meter. Next what I have been given is I have also been given my RL of R. RL of R is equal to 112.78 meter, and I have also been given that the horizontal distance between P and R, this horizontal distance is equal to 127 meter, and I'm going to name this horizontal distance from D to the base of the chimney this as D. So I have so this is everything from I'm going to name this much as E, and this much as F, and I'm going to name this much horizontal height as F, this vertical height as H1, this much height is H1, and this much height is H2. QE is S1 and QF is S2. QE is equivalent to vertical height of for instrument station P, and S2 is equivalent to vertical height for instrument station R. So we have basically written down every information, and this much is equal to our will be equal to our staff intercept. Yes. So next what we are going to do is we are going to draw our second figure for our second part of the question, which says the RL of elevation from R to a vane 2 meter above the foot of the staff held at P was 15 degree 11 minutes. So what this basically means is we are going to held a staff held a vane of 2 meter height at instrument station P, and we are going to sight it from instrument station R. So let me draw this figure. We are going to draw it in this way. What we are going to do is we are going to draw, this is going to be our vane. We are going to have our instrument station over here, and we are going to have a certain, and this is going to be my up to here. So as you can see here, I have been given the angle of elevation from R to a vane 2 meter above the foot of the staff held at P was 15 degree 11 minutes. This is my instrument station R, and this is going to be my instrument station P, and this much height is equal to 2 meters. This is equal to the height of our vane, and I'm going to name this much height in total as H. And I have my distance. This is equal to my small distance D. This is small distance D, and this is also going to be small distance D, which is equal to 127 meter. So next we are going to use formula. Next we are going to use some simple formula of tan to calculate this, and let me write one more data over here. I have my instrument station at R as 1.64 meter. So this is my second figure. My second figure has also been completed. So now let me let me solve this one solution. So firstly, what we are going to do is we are going to find our value. We are going to use this triangle. Firstly, we are going to use this triangle. Let me name this triangle. Let me name this as B. This is R dash, and I'm going to name this as A. So and this much height difference, this much is equal to X, which is equal to H minus 2. I'm naming this much as X. So what we are going to do for this much, this portion is firstly we are going to take the triangle B R dash A. So we have from triangle B R dash A, we are taking this triangle. We are going to use the formula of tan 15 degree 11 minutes equals to H divided by small d, which is equal to 127 meter. Therefore our value of H will be simply equal to 127 into 15 degree 11 minutes, which will be equal to 34.46 meter. 34.46 meter. So I have calculated my value of H. Next what I am going to do is I am again going to use this formula in this way. Tan 15 degree 11 minutes equals to 2 plus X. H is 2 plus X divided by 127 meter. So what we have next is tan 15 degree 11 minutes into 127 equals to 2 plus X. 2 plus S. H is equal to 2 plus X. In next time we are writing 2 plus H 2 plus X instead of H. So I'm going to get my value of X as 32.465 meters. So on solving this, we are going to get the value of X as 32.465 meter. I have written it down directly. Next what I have is I need to write my value of S. Therefore yes, so what is my S? I have written down over here. S is my height difference, S2 minus S1. So let me write over here. This much is equal to S2 minus S1, which is my height difference. This S2 minus S1 is equal to S, which is equal to S2 minus S1, which is equal to our difference of staff intercept as well. I have named S2 minus S1 as S. S2 minus S1 equals to S. So I am naming it this way. So S is simply equal to our 1.87 plus this distance, and this distance is equal to X. This distance below our P. This distance below our P, we have our P over here. Our P is over here. The height below the P and above our instrument axis of R, which is equal to X. This much height is equal to X. So if you are not understanding how this is equal to, how our S is equal to 1.87 plus X, firstly check our previous video on which we have already explained. We have explained our case. We have explained this case where our instrument axes are at different levels, but the difference in level is more, which link you can find in the description box below. In that video I have already clearly described how our S will be equal to 1.87 plus X. But to describe it shortly, from this figure we have calculated our X. Our P is over here, and actually our A is over here. So our A is somewhere over here. This small distance X, which is equal to 32.465, 1.87 plus 32.465. So in order to calculate this x, we have used this figure. We have kept our plane of 2 meter at p. So in this way we find our value of s as 34.335 meter. We have this small distance below p as x, which we calculate from this figure second, and we have our instrument, we have our staff intercept s, or the difference of s2 minus s1, which is equal to s as 1.87 plus x, 1.87 plus x, as you can clearly see from the figure. So let me little bit zoom in over, let me zoom in this portion. We have 1.87 plus x, 1.87 plus x. This much distance s will be equal to 1.87 plus x. We have found the value of x from this figure, from this figure second, and we simply add 1.878 to find the value of s, or to find the difference of s2 minus h1. So next what we are going to do is, knowing the value of s, we are going to find the value of h1 and h2. So next what we are going to do is, from triangle, we are going to use this triangle p dash eq. We have tan 38 degree 21 minutes equals to h1 divided by d. Similarly, from triangle r dash qf, from our triangle r dash qf, we have tan 21 degree 18 minutes equals to h2 divided by 127 plus d. So we have simply we have simply used our formula for tan. So as you can see from our figure, we have used this triangle p dash qe. We have our tan 38 degree 21 minutes equals to h1. H1 is our p, divide our base is d. Similarly, for our triangle r dash qf, we have tan 21 degree 18 minutes equals to s2. This is our perpendicular s2, divided by our base is 127 plus d. So we have simply use the formula tan theta equals to p by b, which we have already used in our various numericals before. So next what we are going to do is, we are going to calculate our value of h1, which will be which is equal to d into tan 38 degree 21 minutes. Similarly, we are going to calculate our value of h2, which is equal to 127 plus d times tan 21 degree 18 minutes. Now what we are going to do next is, we are going to subtract both of these equations. We have h2 minus h1 equals to d into tan 38 degree 21 minutes minus 127 plus d into tan 21 degree 18 minutes. So as I just explained before, we have the difference of s2 minus s1 as s, which is our staff intercept s, and this staff intercept s, we have found this value to be equal to 34.335 meter. So therefore we calculate our s for this reason only, so we can use it instead of s2 minus s1 and find the value of d. And on solving this, what we are going to get is, so let me write this down directly. We are going to subtract the same. Therefore our value of d will be equal to 37.829 meter. So I have written this down directly. On solving this, we are going to get your value of d as 37.829. Therefore our h1, which is equal to d into 37.829 into tan 38 degree 21 minutes. This is simply equal to 29.929 meter. Similarly, our h2, which is 127 plus d into 127 plus d is 37.829 into tan 21 degree 18 minutes. This much will be equal to, our value of h2 will be 64.264 meter. We have found our h1 and s2. So finally what we are going to do is, we are going to find our RL of top of the chimney. We need to find our RL of top of the chimney, and we are going to use the value h1 and s2. So from h1, RL of top of chimney, this will be equal to, we have been given RL of R from our question. We have RL of R, and we are going to add the height of the instrument axis of at R, which is 1.64. So let me add that as well, 1.64 meter. So adding this much, we reach up to, we find the RL of instrument axis of R. So we have reached over here. Since we are going to use S1, we need to add S as well. So on adding S, we reach over here, and we finally add S1, will reach to the top. So let me explain it one more time. I have been given RL of R from my question. Next I am going to add 1.64, then I am going to reach up to the RL of instrument axis of R. Next I am going to since I am going to use H1, my remaining this much distance is yes. So in the RL of instrument axis of R, I am going to add yes, I reach up to here, and from here I am going to simply add H1 to reach to the top. So RL of R plus, so let me simply write over here, 1.64 meter plus yes plus H1. RL of R 1.64, yes, and H1 value is over here, H1. So I reach up to the top. So you can see your figure and write this formula. And I have my RL of R as 120. RL of R is 112.78 plus 1.64. My value of yes is over here 34.335 plus my H1 value, which calculated is 29.929 meter, and this is equal to 178.684 meter. So now from H2 also I am going to find my RL from H2. So let me do this from H2. RL of top of chimney. RL of top of chimney. So I am going to follow the same step. I am going to write RL of R plus 1.64 meter plus RL of R plus 1.64 meter. Since I am going to use H2, I can directly use H2 because H2 is up to here. I don't need to add a yes anymore. RL of R plus 1.64, I reach up to here, and my remaining height is H2, which I know directly, so I can reach directly to the top. RL of R plus instrument height plus H2, I directly reach up to the top. So RL of R plus 1.64 plus H2, and this is equal to 112.78 plus 1.64 and 1.64 plus my value of H2 is 64.264 meter, and this will also be equal to 178.684 meter. So hope this video was of help to you and your concept of trigonometric survey was clear. If you have any queries, do comment down below. And this video took a lot of time to make, so if you like our content, do subscribe the channel and share with your friends. Thank you.